All right, in this chapter, we're going to be looking at balancing of chemical reactions. So it's just the introduction, very first part of actually balancing it. We'll be doing this all throughout the rest of our classes. All right, when we actually have a chemical reaction, what we're actually seeing in a balanced chemical reaction is just how those atoms get rearranged. So a chemical change is defined as something where there are new substances. So it will be made out of the same atoms as before, but we're going to put it together in different orders. And that is a chemical that rearrangement is the chemical reaction. Now, in a balanced chemical reaction, we're going to have two categories. Definitely, we'll have reactants and products. We're going to have the items we start with, and we will show what they turn into. If we're talking about like gasoline in our car, the gas itself is the reactants. What it makes is carbon dioxide and water vapor, and you need a little bit of oxygen with that. But we'll expand on that. That's actually I'm just showing it to make light of that arrow. On the left is the reactants, the things we start with, and then on the right is the thing it turns into, the products. Okay, there is more than just gases being produced to let you know there is a chemical reaction. All of these on this page are actually examples, but they're not the only things. For the most part, we can safely say if you see any of these, though, you are seeing a chemical reaction. So formation of a new solid, and this might be a situation where you mix two liquids together and out comes a solid. That would have to be a chemical reaction. Fifth grade science fair project, when you put vinegar in with baking soda and got the volcano or the simulated volcano, that's actually producing gas bubbles. It's almost the exact same thing as, chemically speaking, as what happens when you put Alka-Seltzer tablets in waters. The bubbles are actually a sign of a chemical change. We do see color changes. One of the more obvious ones of that is just rusting of metal. I mean, if you think about rust spots on steel, it starts out looking like steel, and when it rusts, it actually changes to orangish red color. And then we do have some that just release a lot of heat, and some absorb heat, but the actual just a temperature change can be a sign of a chemical reaction. All right. What we're going to actually end up doing, though, is we got to do a lot of things in a chemical reaction. The first thing is to keep in mind that the mass of the products and the reactants must be the same. There's got to be a conservation of mass. So I have this equation up here to actually get us a starting place. This is just the combustion of hydrogen gas. Burning hydrogen with oxygen makes just water. All right. Well, the law of conservation mass does tell us that if you had the mass of the hydrogen and the oxygen, the mass of the water would have to be exactly the same when the reaction is complete. There can't be any mass created nor destroyed. All right, but that would actually potentially create a problem here, because if we thought about, so hydrogen has a mass of 1 gram per mole. So let's say we had 2 grams of it because the two, and let's say this was 32 grams. The law of conservation of mass would say that this needs to be 34 grams when it's all done. But we find out that's not what will happen here, because technically speaking, there's not enough oxygen to get this to go to completion. It's going to actually stop, and we're going to be left over with still some hydrogen. So the reason I know it's not going to go to completion is because if we think about this on just the sheer number of atoms over here, on my reactant side, I have 4 atoms. I have 2 hydrogen atoms. I have 2 oxygen atoms. On my product side, I'm only showing 3. Now, I can't just come over here and put O over there, because that's not what happens in the chemical reaction. The chemical reaction has just hydrogen and oxygen as reactants and just water as products. So we're going to have to actually change the number of atoms with coefficients. And we're going to see this, we're going to practice this all throughout this thing. But technically all we're going to do is, see how I say there's 2 oxygens? Well, each oxygen makes 1 water. So we must make 2 waters from that O2. And then to balance that out, we need to actually have 2 hydrogens. And that's actually what ends up happening. We actually see that the amount of hydrogen compared to the amount of oxygen, there's twice as much hydrogen that goes into water as oxygen. But our chemical reaction is going to show that. So Rather than try to do this by masses, we're just going to see something very simple. The atoms present in the reactants must still be the exact same atoms and the exact same number of atoms in the products. So the actual atoms, so see how this has 4 hydrogens and 4 hydrogens and 2 oxygens and 2 oxygens? All equations will have the same number of atoms on both sides. And we're going to always take care of that by changing the coefficients. Can't change the molecular formulas without changing what the actual molecule is. And we're not allowed to do that. Chemical reaction defines what the actual molecules are. All right. Next thing we're going to do, when we actually balance it, we're going to have whole number there in front of it. Can't do fractions, so it has to be whole numbers, and we want the smallest possible whole numbers. These other two things are just going to help us actually do the balancing, so we're going to actually apply these other two here when we actually start practicing balancing of equations. All right, so got 3 things that we're putting in there: reactants and products and those coefficients. Now, we already talked about the arrow, but we're going to see that there's sometimes we put little weird things on the arrow. For instance, in swimming pools, we put chlorine and we dissolve it in the water. And to make it actually do something and actually clean the water, it actually goes through a chemical reaction and it turns into what we call free radicals. So I just put a single dot there to show there's an unshared electron on that chlorine. And it actually makes 2 of those, one for each one of these over here. All right, that is just what happens in our pools to actually make the chlorine work and disinfect the pools. Well, it turns out to get this to happen, we need to hit this thing with light. And so on those arrows, you will actually sometimes see things drawn on top of the arrow to indicate something else you have to add. And then this last thing, the physical states, well, that's what I just did there. I actually defined the chlorine as being dissolved in the water, and I've defined their radicals as being dissolved in water. And that's what aqueous means. Aqueous just does mean dissolved, and then solid and gas mean the same thing they did back in elementary school. All right, so those 5 things need to be in balanced chemical equations. All right, so when we come up to an equation like this thing here, I got CH4 and O2 and then CO2 and H2O. The first thing we want to do to make sure it's a good equation is to check the number of atoms on both sides. We're going to balance the equation. And right now we have 1 carbon and 1 carbon, 1 carbon and 1 carbon, 4 hydrogens, only 2 hydrogens. We have 2 oxygens on this side, but we have 1, 2, 3 oxygens over there. So we're not balanced. We have an imbalance of the number of atoms on both sides. All right, but we actually can fix this by actually just going through a very methodical process. We're going to actually use our atoms from left to right and balance them out. So we do look at the carbons and we see they're fine. The next thing we're looking at is the hydrogens. See how there's 4 here? So I'm going to come over here, and since this is the only molecule that has hydrogen in it, I'm going to get this one to have the right number of hydrogens. So I'm going to put a 2 in front of it. That will give us those 4 hydrogens. And now we're to our oxygen. Now, I would normally skip oxygen until it's the last atom to balance, and I do that in this case because it's found in 2 products. So there's 3 reagents that have oxygen in it, but we've actually taken care of everything but the oxygen, so it's now time to balance the oxygen. So I have 2 oxygens from this, and I have 2 more here. Give us a grand total of 4 oxygens. So I would need 2 of these. Now, technically, the picture down below is just another way of doing that. It's actually more of a symbolic method, but we are just going to do the same thing. You want the number of atoms on both products and reactant side to be the same, and you're going to fix those by changing those coefficients. All right, let's look at another one. Oh, that is that same one. Could have actually just went to this page. All right, so here's our steps. When we actually write a balanced equation, the very first thing we're going to want to do is put down our reactants and products. Sometimes we'll be able to put their states down right away because we might see a problem that says you're putting oxygen gas in, or it makes CO2 gas. So if it says what the state is, you write that down as you write down the formula of the chemical product or reactant. All right, once you have those, your next step is actually to balance it out. So you're going to be writing down your element compositions of, or you're going to be writing down the chemical compositions of the molecules and elements in step one. And in step two, you're getting it ready to be balanced, because in step two, it should just be a overall equation that shows the species that are in there. Step three is where we actually balance it. And that really does mean you go through and you add coefficients to get the um, number of atoms to be equal on both sides. All right, so let's practice that with a word one. So I got one here. It says we're going to take lithium metal, react it with water to form lithium hydroxide and hydrogen gas. All right, so I'm going to start with the lithium metal. And metal implies solid, so I'm putting down solid. And it says water. Now, it doesn't say the phase of water, but you know, if you think about it, most of the time we're probably going to call solid water ice, and vaporized water or steam, we're probably going to call it water vapor. So typically when you just see water, it is liquid, and it is in this case. All right, these two go and react together. They form lithium hydroxide. And I have to look at the charges here on our ion because that is an ionic molecule. Lithium always forms a positive ion, and hydroxide forms a negative. So lithium hydroxide will just be LiOH. And then last thing is hydrogen gas. Now, something that could have been beneficial here with lithium hydroxide. If you saw this on something like our test, I would actually say aqueous lithium hydroxide, because we're really not ready to be able to tell you you have to predict what form lithium hydroxide would be in. But lithium hydroxide is an aqueous substance in this case. It's going to be dissolved in that water that's already in there. All right, so now we just got to look at it and figure out how to balance it. Our lithiums are okay. Hydrogens are not. We got 2 hydrogens here, but we have 3 over here. Right now, oxygens are okay. All right, but I flat out just don't have enough hydrogens. And worse, on this side, I'm going to have an odd number of hydrogens if I leave this with a 1 in front of it. And I would need even numbers to get even number in the waters for the 8 because they come in 2s. So I'm actually going to back up here and put a 2 in front of that, so I have an even number of hydrogens. Now that does mean I have to come back here and change this, and it also created 2 oxygens, so I need to actually change this. But now we'll be able to take care of the hydrogens because I have 4 hydrogens. This gave me 2, and there's another 2. So we have a balanced equation by putting those coefficients there. All right, another one of these. I didn't put phases here. We're going to leave those off on this one for right now. I mean, we can answer 2, maybe 3 of these and say for sure what phase they are, but the NO is one that I would tell you in some case. All right, but right now we're going to do our coefficients. So I have 1 N and 2 N's. So I'm immediately changing that to a 2 because that gives me my 2 nitrogens. Now I have 2 oxygens, so I need 2 waters because of those oxygens. And that created 4 hydrogens, so I need 4 hydrogens. All right, now how I worded this, there is no reason right now for you to know what state that is. NO is not something that's common, so you probably would not know at this time if it's a solid, liquid, or gas. So if I were giving you a problem like this on our test, I would somehow tell you the phase, or I wouldn't actually be checking it. Now, hydrogen you should be able to predict. Most of our diatomic nonmetals are gases at room temperature. The only exception on the entire periodic table is Br2, and it is a liquid. And in this case, water could be multiple things. There's no reason to believe it couldn't be a solid, liquid, or gas because those all exist in the air right now. But we're going to put it down as a liquid right now because that's where we typically find water at room temperature. All right, another one of these. We're getting a little bit more complex because I have a slightly bigger molecule. And to be honest, this is a little bit more like how I might ask the question on a test, because you notice how it just asks what the coefficient is in front of the Fe. So we would just be looking for that number. Now, when we start going left and right, you might immediately see that 2 and put on a 2 and you think you got it done. But we're going to find that's not right, because if you notice how this 3 oxygens, there's no way I'm going to take care of 3 oxygens at 2 at a time. It's because of that, I need to back up here and put a 2 in front of that. All right, so that means I would have 4 irons. Now, that 2 times that 3 gives me 6 oxygens, so I need 3 of these. And then I need 3 carbons. But we would be balanced now. And we have a problem that has coefficients in front of everything. All right, and we're not going to worry about the phases on this. We'll do that here on a couple more, and a few more problems. All right, this is a slightly more complex one because I've got a lot more going on. All right, but we're going to do the exact same steps. I have 3 magnesiums. I need 3 Mg OHs. I have 2 nitrogens. I would need 2 ammonias. All right, I'm leaving the hydrogens alone because they're in 2 different reactants or 2 different products. Well, I can take care of the oxygen. I have 3 times 2 oxygens, so I would need 6 of these. All right, does that take care of our hydrogens? I have 3 times 2, 6 hydrogens. 2 times 3 hydrogens, another 6 hydrogens. So 12 hydrogens there, 12 hydrogens here. So it's balanced. You notice we're just going left to right. Now, you can go almost in any order, but just make sure you're checking every single atom. That is why I go left to right, because then we don't miss any. All right, another one of these. Aluminum sulfate with potassium hydroxide giving us aluminum hydroxide in KSO4. All right, we're going to sometimes do these slightly out of order. Rather than go left to right on these, I would probably start with this more complex one because there's a lot more going on. And what I mean by starting with it, you see how it's got 2 aluminums? I'm going to come over here and take care of those 2 aluminums. And I'm not going to do anything with these OHs yet. I'm going to go right back here to that sulfate again. And I have 3 sulfates. I'm not saying that's 3 sulfurs and 12 oxygens. I'm going to leave it as a sulfate because if you look over here, it's still a sulfate. It's not falling apart. We're going to count it as a whole group. So 3 sulfates, I would need 3 of these. And now it makes this work out a lot easier because those 3 times those 2 potassiums give us 6 potassiums, or 2 times 3 hydroxide give me 6 hydroxides. And now we have a balanced equation. All right, last thing, we're going to actually introduce more or talk more about those phases. So there's only four things that we see in parentheses after those, and these that really should be in italics, but it's okay if they're not. You see solid, liquid, and gas, and aqueous. And aqueous for now just means dissolved in water. And these phases will sometimes be things that you know, like our small little diatomic molecules are typically gases. CO2 is something in our atmosphere we know as a gas. Water's a liquid. Almost every single metal is a solid with the exception of mercury. And almost every single ionic compound, so made with a cation and anion, are solids at room temperature. So we have certain things we can predict, but typically what I do to get you to have the phases correct, I give you pictures or I use the words to make sure you understand that it is a solid, liquid, or gas. So on this one, it says, write the chemical equation for that reaction that's above, which is potassium reacting with liquid water, producing hydrogen gas, and aqueous potassium hydroxide. All right. The only thing that's kind of tricky here, it just says potassium. Doesn't say if it's solid, liquid, and gas, but it does refer to that picture. And it's probably safe to say that that stuff is the water, and these other things are the potassium, and therefore the potassium must be a solid, because that's why it looks like that. All right, so the solid potassium reacts with liquid water to produce hydrogen gas, H2 gas, and potassium hydroxide, KOH, that is aqueous, AQ. So we know our phases because of the clues we gave in the problem. Now we're just doing what we did before, and we're actually making sure everything balances out. So I have one potassium, two hydrogens, three hydrogens. Even number of hydrogens over here, so I'm going to start by doubling that, which would mean I need to go back here and double this. All right, now I have two hydrogens, but over here I have four. So I'm going to put a 2 there. That gives me two oxygens and two oxygens. So we are balanced. All right, another one of these. Almost looks like the same type of thing, but if you notice, this is a nice little like a ribbon. But it tells me we're going to take solid zinc, add it to aqueous hydrochloric acid, produces hydrogen, gaseous hydrogen, and zinc chloride. All right, so zinc solid reacts with hydrochloric acid. Hydrochloric acid is hydrogen chloride gas dissolved in water, so HCl aqueous. And that goes forward to form, and it says gaseous hydrogen and zinc chloride. I don't just want to write down just zinc chloride, because zinc always forms a positive 2 ion. Chloride's always -1. So zinc chloride is definitely ZnCl2. And it does say zinc chloride remains dissolved. So zinc chloride is aqueous. And now balancing it, zincs are fine. Hydrogens are not. So I'm going to put a 2 here, and that takes care of my chlorines too. All right. How about just words? Magnesium metal burns in air to produce a white powdery compound, magnesium oxide. All right, it does say just burns in air, and technically there's a lot of things in air. There's oxygen, there's nitrogen, there's some water vapor, there's carbon dioxide, and there's other things. But typically when you burn something, and we kind of do know this, you need oxygen. That's why they throw water on fires, because that water removes the oxygen from the fuel. All right, so it is going to be magnesium and oxygen. It is going to be a gas. It is magnesium metal, so a solid. And it tells us it forms magnesium oxide. Magnesium is always a 2+. Oxide's always a 2-. That's going to form MgO. And like many ionic compounds, that is a solid, but it actually does tell it's a powdery compound. All right, balancing this, the Mg's are okay, but the O's are not, because I got 2 of them. So I'm going to come over here and put a 2 in front of the MgO, then back up and put a 2 in front of that Mg. Okay, another one. 1,000 degrees, so very hot. Ammonia gas reacts with oxygen to produce gaseous nitrogen monoxide and gaseous water. All right, so ammonia gas reacts with oxygen gas to produce nitrogen monoxide gas and gaseous water. A bunch of gases. All right. My nitrogens are okay, but my hydrogens never will be, because odd number and even number. So I'm going to back up and put a 2 there, which means I would need 2 NOs. Now I have 2 times 3, 6 hydrogens, so I need 3 of these. And that gives me 2 oxygens plus another 3, so 5 oxygens, which I can't do here because I can't get an odd number of oxygens. So back up, change this to a starting number of a 4. And that does mean we'll be changing that to a 4, and the number of waters, because 4 times 3 is 12, is actually 6. But now we have 4 oxygens and 6 oxygens, gives us 10 oxygens, so we need 5 O2s. Has coefficients in front of everything. All right, another one of these. I have solid ammonium nitrate is heated. When it heats up, when you heat up ammonium nitrate, it produces nitrogen gas and water vapor. It's actually borderline why this stuff can be dangerous. Why we do end up using it as fertilizer. If it gets hot too fast and it produces a bunch of gas, that is potentially an explosion. All right, so ammonium nitrate. Ammonium is NH4 plus, nitrate is NO3 minus. So ammonium nitrate is NH4NO3, and it is a solid. And when it heats up, it produces nitrogen gas into gas and water vapor, H2O. Oh, I got to fix something. I was going to say this is not going to work out. I actually have put down nitrate here, and I actually think I said nitrate, but that says nitrite. That needs to be a 2. That's the only difference between nitrate and nitrite. That's going to work out better. All right, now I have a nitrogen and a nitrogen, so 2 nitrogens, 2 nitrogens, 4 hydrogens, so I would need 2 waters, 2 oxygens, 2 oxygens. Now, phases. So solid gas, water, vapor, gas. Now we're balanced. All right. Now, you're going to get a chance to practice this on worksheets. We're going to do a couple more of these. If you have problems, make sure you email me or ask questions. All right, so we got liquid nitric acid decomposes to a reddish brown nitrogen dioxide gas, liquid water, and oxygen gas. It's actually kind of cool looking. It actually is a very, very dark reddish brown. So liquid nitric acid, HNO3. That is supposed to be a 3. It looks terrible. And liquid, so it's actually better call that aqueous, because HNO3 is dissolved in water. All right, that decomposes to a reddish brown nitrogen dioxide, NO2 gas, liquid water, H2O liquid, and oxygen gas, O2 gas. All right, going from left to right, I have 1 hydrogen. Over here, I'd have 2. I'm going to change that to 2. 2 hydrogens, now 2 hydrogens. 2 nitrogens, 2 nitrogens. All right, now I normally would save the oxygens to last, but the only thing I have left to take care of is oxygens. I have 2 times 3 oxygens on my reactants, so it's a total of 6. 2 times 2, 4, 5, 6, 7. So I have too many oxygens on my product side. So when that happens, we just back up here and increase the number of HNO3s. We're doubling them. Now that does mean we end up doubling this value that we put there. It's not 2, it will be 4. And let's see, 4 hydrogens, I would need to double this. And now I have 4 times 3 oxygens, 12 oxygens, 8 oxygens plus another 2, 10. To get the 2 more, we just need 1 O2. So that is now balanced. And pretty sure that, yeah, 2 more, and then we're done with our practice ones. All right, so we're going to do another one of these. Phosphorus trichloride can be synthesized by combining its elements. All right, so by synthesizing, telling us that we're going to make phosphorus trichloride. and we're going to make it from its elements. So that means phosphorus and chlorine. All right, interesting. I didn't really give you enough information to know for sure what the phases are. Also, didn't really tell you the format of the phosphate. We don't typically find phosphate by itself, though. Hold on a second. I had to cough there. All right, so phosphorus is typically, when it's found as P4. So 4 of them in a nice little complex, and it is actually often found as a solid. Now, neither one of those you would have known because of how this question is worded. So I would actually change that for us when we actually get to the test. Now, chlorine, you might know it's a gas because we're going to see that one a lot. And phosphorus trichloride is a nice little solid when it's all done. So we would know our phases somehow. All right, but the P4 does tell me I need to get 4 of these, which is going to give me 12 chlorines. So I would need 6 of these. And our last one, we have liquid pentene. Now, it turns out pentene is related to stuff in your gas tank. One of the smallest carbon-containing compounds in your gas tank is pentane, with an A there. But pentene is found sometimes. Typically burns a bit too hot and has too low of a boiling point to make it into a gas tank, our regular old gas. All right, but if it were to burn in air, in this case, that is going to be O2. It is going to make carbon dioxide and water vapor. Carbon dioxide is definitely a gas. Water vapor, gas. Oxygen is the air, so it's a gas. And it does say liquid pentane. All right, we're just doing the same thing we've been doing, left to right. So I have 5 carbons, make 5 CO2s, 10 hydrogens. So I'm going to make 5 O2s, or H2Os. Now that gives me 5 oxygens. This would give me 10 oxygens, so 15 oxygens. I can't do that here because this is an even number. I'm going to back up, change this to a 2. Change both of these to a 10 then. Because 2 times 5 carbons is 10. 2 times 10 hydrogens is 20. And now we have 20 oxygens plus another 10. We would need 15 O2s. So a whole bunch of molecules to do that. But that is now balanced, has our phases, looks awesome as a balanced equation. All right, have fun practicing these.